427 days into what began as a 30-day mission, everything changed. A brief tech demo had transformed into a tale of survival and resilience. On the barren surface of Mars, nearly 297 million kilometers from Earth, a tiny 680-gram helicopter named Ingenuity kept going. Built from consumer-grade parts, including Android phone components and drill batteries, she far exceeded expectations. But now, something's wrong. Mars is entering a brutal winter. Nighttime temperatures plunge to 85 degrees, and massive dust storms darken the skies. On day 427, NASA's Jet Propulsion Lab, JPL, attempts contact. Silence. No signal. Repeated pings yield nothing. The team fears the worst, that Ginny, the first aircraft to achieve powered flight on another world, may have shut down for good. 6 years earlier, I saw Ginny at JPL. Even then, her mission was doubted. Kenneth Farley, chief scientist for Perseverance, had opposed it, calling it a distraction. The $80 million budget, less than the cost of the Martian movie, seemed too small to matter. But a committed team of engineers pushed forward, aiming to prove flight on Mars was possible. On February 18, 2021, Perseverance landed on Mars. Attached to its belly was Ginny. That was Sol 0, her first Martian day. Soon detached from the rover, Ginny's goal was clear: fly in Mars' thin atmosphere. But that's no easy task. The air is only 1% as dense as Earth's, making lift generation extremely difficult. To succeed, Ginny had to be ultralight, with rotors spinning at 2,400 RPM, far faster than Earth helicopters. Over 2 months, her systems were tested: engines, navigation, computers, preparing for the big moment. Then came Sol 58. The blades spun. Ginny lifted off. Just 120 years after the Wright brothers flew, we took flight on another planet. It was a milestone. Within days, she flew again, and again. 5 flights in 1 month. The original mission was complete. That should have been the end. But her success opened new possibilities. NASA extended the mission. Ginny became a scout for Perseverance, flying into areas the rover couldn't safely explore. There was no roadmap. Each new flight pushed boundaries. As one engineer said, after Flight 5, we could have died on Flight 7 or 10. Previously, every maneuver had been simulated and planned in detail. Now, Ginny had to navigate uncharted terrain with minimal data and zero room for error. Remote control wasn't possible. Mars is too far, over 56 million kilometers, creating a 6-minute round-trip delay. With each flight lasting just 2 minutes, all operations had to be fully autonomous. Here's how. Earth-based pilots program a flight path. Then Ginny takes over, calculating, adjusting, and flying on her own. But first, she must know exactly where she is. Unlike Earth, Mars doesn't have GPS. Only 7 orbiters exist, with no consistent coverage. Instead of GPS, Ingenuity relies on a simple yet clever navigation system using 2 cameras, a 13mm front-facing color camera, and a downward black and white navigation cam capturing 30 frames per second. Her onboard computer analyzes surface features, rocks, shadows, ridges, in real time, tracking their movement between frames. It's like an optical mouse, detecting motion based on shifting surface patterns. This system lets her estimate position and direction, but it's not perfect. Low-contrast terrain or dust can confuse the algorithm, and errors may accumulate. On Mars, one mistake can mean disaster. Flight 6 was her first real crisis. Leaving her familiar zone, Ginny began to wobble just 54 seconds in, tilting up to 20 degrees. The cause? A rare camera sync error. The flight system depends on perfect timing between the navigation and color cameras, but a color image was captured almost simultaneously with a nav image. Because the color camera was added late in development, compatibility was limited. The system dropped the navigation frame it needed, causing all subsequent images to be delayed by 1 frame. This created a loop of miscorrections. The system thought she was lagging, overcorrected, and the instability worsened. A crash seemed imminent. Thankfully, Ginny landed safely, and engineers at JPL identified the bug. They issued a software patch to fix the sync issue. She was back in the air and would go on to fly many more times, supporting Perseverance's mission. But new challenges soon arrived. Right before Flight 19, a severe dust storm hit Jezero crater. Winds reached 20 meters per second. The flight was canceled, and the team waited in silence. After 6 long days, contact resumed. Ginny had survived, but not without damage. Martian dust became a constant threat. It reduced her solar power by 18% and began jamming servos. The team had to cancel the initial flight attempt and improvise, accepting less power and wiggling the joints repeatedly to dislodge dust. Ingenuity was still flying, but she was battered. Temperatures added to the struggle. Mars has almost no atmosphere to retain heat. Nights plummet to 133 degrees, with wild temperature swings even during the day, from 23 degrees near your feet to freezing at your head. This cold drained Ginny's energy fast, straining her survival systems. If you're curious how extreme temperature swings spark Martian dust storms, check out Astrom's deep dive on the topic. But for Ginny, the challenge now was survival. As Mars drifted farther from the sun, its winter grew harsher. Nights got colder, threatening Ingenuity's electronics. Many of her systems were hand-soldered, and constant temperature changes could crack the joints. Worse, if the battery electrolyte froze, it could stop working permanently. So engineers created the warm box, a small enclosure housing critical systems with resistance heaters to keep temperatures above freezing at night. But that came at a cost. Only 25 to 30% of her battery was used for flight. The rest went into staying warm. As the nights worsened, heaters consumed more energy, risking a cycle where the battery couldn't recharge enough to power the heaters, leading to total shutdown. Then came May 3rd. At JPL, the team began their routine check. No signal. They pinged Ingenuity again. Still nothing. Silence. The room grew tense. Had Ginny gone dark forever? Instead of giving up, the team reviewed every possibility. They remembered Ginny's design. An internal alarm clock wakes her each morning for 15 minutes. If no signal is received, she goes back to sleep. Their hypothesis: her batteries had drained overnight, shutting her down. But with sunlight, she might slowly recharge and reboot, with a reset clock. If so, her new wake time was around 11:45 a.m. Martian time, not when they'd been pinging. They adjusted accordingly. Ping after ping, then a response. She was alive. Most components in the warm box had survived freezing, even though they were only rated to 45 degrees. But one system was lost: the inclinometer, which tells Ginny her orientation before flight. Without it, she couldn't safely take off. The team was stunned, but then inspiration struck. Ginny was built using smartphone tech. Her processor came from a Samsung Galaxy S5. Some sensors were from a Google Pixel 3, and smartphones include motion and orientation systems. Inside every phone are MEMS, micro-electromechanical systems, arranged along the X, Y, and Z axes, tiny masses supported by spring-like arms. Following Hooke's law and Newton's second law, they measure force and displacement, A equals kx m. As the mass moves, the capacitance changes, producing measurable data. These are accelerometers, which can determine motion by converting mechanical movement into electrical signals. When you integrate acceleration, you get velocity and position. Add in a gyroscope, and you have an IMU, inertial measurement unit, the same system that powers screen rotation, mobile games, and fitness tracking. Ginny had one on board. At first, the damage didn't make sense. Ingenuity's broken rotor blades looked too clean, with no signs of crashing into the ground, no debris, no gouges. It didn't feel physical. So what really happened? Picture a spinning blade tracing a circular path like a hula hoop in the air. When a force is applied to part of that spinning loop, the response is delayed. Due to gyroscopic precession, the maximum deflection happens 90 degrees later, not at the point of impact. It's the same principle you see when spinning a bicycle wheel. Ingenuity had two sets of counter-rotating blades to cancel out torque, but each blade still flexed under precession forces. That flexing creates stress, especially where the blade's internal reinforcement thins. That's exactly where the fracture occurred. Crash photos show a jagged break near the tip of the rotor. During Flight 72, Ginny descended at an angle and struck a soft dune. The impact traveled up the frame, inducing torque and snapping the blade at its weakest point. And yet, everything else survived. Landing gear, avionics, servos, all intact. The rotors were the only failure. That insight is shaping the next generation of Mars helicopters. Chopper. The new blades are stronger, reinforced for higher torque and rougher landings. But Chopper doesn't just upgrade durability, it transforms capability. With 6 rotors instead of 2, it can lift more and carry real scientific instruments. For the first time, a flying vehicle on Mars won't just scout, it will do science. Chopper also features a lightweight radio system capable of direct communication with Mars orbit. No more relying on rovers like Perseverance. Chopper is fully independent, free to explore the planet on its own. This opens up a new era. Imagine carrying 5 kilos of scientific equipment across 3 kilometers per sol in just minutes, faster and more agile than any ground rover. Planetary scientists are already thrilled by what comes next. Even Chopper's landing method is revolutionary. No sky crane or complex tethers. Instead, it launches mid-air from a delivery platform descending through Mars' atmosphere. Retro rockets slow the descent, then Chopper detaches and flies. No wheels, no cables, just flight. Now the vision is clear. Fleets of airborne explorers flying over Martian canyons, volcanoes, and polar ice. Mars could one day have airports, supporting larger, more autonomous aircraft. And it all began with a tiny $80 million prototype that few believed in. NASA once doubted Ingenuity. Now she's inspired a revolution. It echoes the early days of flight on Earth. In the late 1800s, dreamers were ridiculed. Then came the Wright brothers. Suddenly, flight was real, possible, inevitable. That spirit lives on in Ginny. Still attached to her belly is a 1 square centimeter scrap of muslin, cut from the wing of the original Wright flyer. From the first flight on Earth to the first flight on Mars, history completes a poetic arc. Yes, Ginny crash-landed. Her blades are gone. But she's not done. Today, she still runs as a Martian weather station, capturing daily images and recording temperature data. Built for 30 days, she flew for almost 3 years. Even in retirement, she continues to work, defying expectations to the very end. Ingenuity wasn't just a tech demo, she was the proof, the spark. And now, the sky above Mars is no longer silent. If you've been inspired by Ingenuity's incredible journey, from impossible dream to Martian milestone, don't just watch. Be part of the mission. Subscribe to Space Future now for more stories that explore the edge of science and the future of spaceflight. Leave a comment below. What would you want a future Martian helicopter to explore? And share this video with someone who still believes Mars is science fiction, because Ginny just proved it's already science fact. The future is flying, and it's happening now, on Mars.